Okay, let's go ahead and take a look at Module 14.2. We're going to study something called correlation and regression as it relates to the scatter plots that we learned about in the previous module. So we're going to take our two quantitative variables, right, and we're going to go ahead and calculate the correlation between those variables. We call that the correlation coefficient. This is statistics. We learned to get a lot of values, right? We've got different kind of statistics before. This is another one that measures the relationship. How strong is the relationship, right? That was language we used previously in the last lesson around figuring out how strong the relationship is between the two variables. Is it strong? Is it weak? Moderate? No relationship, right? And what we do is we're interested in providing a numerical value, a value that tells you, if I see that number tells me how strong the relationship is. That number is called the correlation coefficient, or just the R value. That's the way we would get it, the value of R, right? And so there's a statistical formula that's used. We don't do it by hand. We use ArtStat to calculate the correlation coefficient. That number is always going to be between -1 and 1, and it tells us the strength and direction of the linear relationship between those two variables. That's what we're introducing right now. Now there's other characteristics of the R values you can kind of talk about here. So always between -1 and 1. Negative means negative associations. Positive value means positive associations. Now, these two pictures aren't in the notes, but I put it here. You might want to take time to kind of copy this down and put it somewhere and say, here are some examples of scatter plots and the value. And so you could, on our online homework, you will see some examples here at this location using data set and a video there so that you could see how to calculate your correlation coefficient. So that's inside the homework right here. So you can go ahead and take a look at that. I just want to overview again, looking at these two relationships here, you'll see an R value. So I want to pay attention to the R values here. You will see that the R values, +1, perfect correlation, not just strong, but perfect. Here are some other words we might highly positive correlation. Some other words, again, I would probably use for this one. I would probably say strong also. Here, to me, this would be moderate. Just to give you some language that we use in the previous lesson. Again, there's a lot of different words people use to describe the strength. That's why we need a number instead of just using words. A number tells us the strength of the correlation. Here are some examples of negative. Now, these are linear associations, again, because they're kind of going in a line, right? They're not non-linear like we've seen in a previous example. And so you see the negative R value. R values here. And then what do you think if we had a graph now? So we have some positive and negative. What would a graph look like? Or what would a scatter plot look like if there was no correlation? I want you to think about that real quick. What would it look like if there was no correlation? There it is. Let me bring it in. This is kind of where the graphs just randomly, no correlation, right? Points are just kind of randomly right there. There's no association. There's an example here. Right? No, where is it right here? The value of R equals 0, no association right there between those two variables. As we look at that, oops, I wanted to use yellow, but that's okay. So we can see that no correlation here. It's just the scatter plot, randomly scattered points. And that's, I think, one of the characteristics you'll see of no correlation here is that you have just randomly scattered points, right, which then leads us to say no correlation. So important to take a look at that, okay? So what do we do now once we know there's a relationship? That's the next piece. Once we know there's an actual relationship between them or correlation, right, we want to then use, right, we want to then use that relationship to be able to make a prediction. And that's the question here. How can we make use of this relationship? Well, when the relationship's linear, it should make sense that we can now draw a line that describes the relationship, kind of like we're here. And that's called the line of best fit. And we have a very technical name for that. It's called the least squares regression line, LSRL, least squares regression line. We may just say the regression line or regression equation. But this comes from an algebra. So this is the little bit of algebra you need to remember, right? And maybe a few years since you remembered it, but you may remember this equation of y equals mx plus b. Right, it's from an algebra class. M is the slope, b is the y-intercept. Well, those numbers mean something. Okay, the slope helps us describe the relationship between the numbers. The value of the slope does that for us, okay? Helps us estimate or make a prediction between the prediction about one of the variables. Now in statistics, instead of writing y equals mx plus b, many times you will see it this way. Y hat equals a plus bx. A represents the y-intercept, which we'll talk more about. B represents the slope. The slope, again, is the way we describe the relationship, this relationship between the two variables. The hat here is confusing to students, but all that represents is that we're using, this is an equation we're using to estimate or predict the value of y. That's it. It's an estimate or predicted value of y, not the actual value. Because we're going to have data and we want to then make a prediction about future values. And so you will see it this way. Or you will see it, the equation done in words like this. Okay, let's predict the weight of someone if you know their height. That's the relationship we have here. We can predict a person's weight if we using their height. There should be some relationship, and these are the numbers, rounded numbers, right, related to that. And again, from our homework, online homework, you'll see some videos about how to use a data set and how to generate this equation, right? You will go to, again, that one, I'm not going to do it, but you will go to the correlation here. I'm just going to briefly show you because the other videos show you how to do that, right? So here are some data from the textbook here. So you will see these two variables here, and you'll see here's the scatter plot between them right here. Oop, no, wrong one. That's a relationship between two variables. I want linear regression. There we go. And so you will see here, there is the data. You can see a whole bunch of other little things going on here. You could type, show me the regression line. And then the equation is here. You're getting the intercept and you're getting the slope right here, those numbers. So that becomes the equation, right? There's a lot of other options here to use if you want to fool around with it, right? But you end up getting your linear regression equation right here to just give you the slope. There's also tells you the strength, right, of the relationship, and that number there gives us the strength of the relationship as we have the data here. And there's other stuff you can do, find your predicted values, what I was talking about, and we'll talk about that. So we'll play around with that in class, but I want to make sure you're taking care of there with that, so that you can fool around with. No one's going to hurt by you playing around with that. But that's how you would generate the equation once you have the data in, right? And that's what the video on the homework does. Now we need to push a little further. And now what do we do when we have the equation? What happens after we have the equation? We need to interpret. I could say that. What do those values mean? What does the slope represent, and what does the y-intercept represent? The slope represents what we call a rate of change, how the two variables are related to each other. As one variable changes, what happens to the other one? Remember, we had that conversation in the last module about increasing. Something increases, the other one increases. If something increases, one decreases, right? Those negative and positive associations, and that's what the slope is telling us. Also, it's not the R value. The slope is not the R value, but it's specifically telling you the relationship between those two variables. It represents the predicted change in your y variable for every change in our x variable, okay? And more specifically, the y-intercept tells us what is our predicted y value if for some reason our x value is equal to 0, some starting value. So again, let's look at, right, how we make these predictions. And as it says here, we want to emphasize that since this is for a regression line, these values represent changes in our predictions or estimates, right? It's not the actual change of the values. These are our estimates or predictions. So as you can read here, with this equation, if we ended up with an equation like this with certain data, which we don't have the data, okay? But if we ended up with an equation like this, you can see, again, you could write it different ways. If we ended with an equation like this, we would say for every 1 inch increase in height, we predict or estimate an increase of 1.095 pounds of weight. That's kind of the average relationship we would predict, right? So as someone gets taller, they would get heavier. And the y-intercept interpretation is if you had a person for some reason be 0 inches tall, we would predict they would weigh negative 100 pounds, which doesn't make sense. And you got to read this note here, that sometimes the y-intercept may not make sense in the context. And that's okay. The least squares regression equation, right, really is a good predictor for the values we have, not for values that are really far out or for the future or in the past. So you just got to keep that in mind. Okay. And then to finish this section off, we look at an idea called residuals, which comes from a prediction. And let's go ahead and do another example of a prediction. So here's some data, right? Someone does their test, a pre and post test, right, to their students. An SAT prep class, for example, right? You want to train students to say, you're going to score better. Well, let's see how much better they would score. Here is an equation from the data. There was a typo here, so it's 0.9846. And so we have an equation, a relationship between those variables. And I'm using rounded values here. So what would our estimate be or prediction be for a student who scored 75 on the pre-test? Well, again, these are actual values, but what would our prediction be, right? Well, you take 75 and you substitute it in for x. X is the pre-test, y is the post-test. And when you do that, you get make sure you're using the calculator and typing this in correctly. I get 86 points. So I would predict 86 points, a prediction of 86 points for someone at 75 on the pre-test. And again, that's just based off of the actual values. These are our predictions. Then that leaves us with, what do we do with these predictions? Well, there's a concept called residual, right? A residual, right, is the observed value minus the predicted. How far is the predicted away from the observed value? So sometimes we call it ROP, and to remember it, residual equals observed minus predicted. So it's just a subtraction, a calculation that we do to get that. And so you can see the math here that's done for this observed and predicted. I calculated the predicted value for 37, a score of 37. We see a predicted score of 49.508 points. So if someone has a pre-test of 37, we would predict 49. Now in this case, we had an observed value of 37 and 54. So 54 was the observed value, right? So we would then, in our calculation, subtract the observed minus the predicted, and then come up with the interpretation, which is the student scored 4.492 points higher than predicted by the least squares regression line or equation. We start to use that. So again, this is an introduction to lesson 14.2. You got some more guidance in the homework, and then of course the practice with the homework problems.